So in this session, I'll talk about a method of integration known as differentiation relative to a parameter. Now, this method is usually employed to integrate a bivariate function as a function with two variables, but with respect to one of the variable quantity. The other variable is treated as a parameter and therefore remains constant during the process of integration. Now, the method involves changing the given integral in the family of integrals and then using some properties from the family of differentiation in order to work out the integral. And I'm going to take an example. I want to evaluate the integral from 0 to 1, x squared minus 1 divided by logarithm of x. We want to integrate this with respect to the variable x. Now, in order to evaluate this, we are going to introduce another variable, t. And so we are going to consider an alternative integral where we replace the 2 here with t, so that we have the integral from 0 to 1, x raised to power t minus 1 divided by logarithm of x. So now in this case, when we work out this integral, we can then replace t with 2 to have our integral, our function back. Now, this new variable will not take part in integration, so we shall regard to this as a parameter. So we shall now utilize the properties of differentiation to solve this function, to solve this problem. So first, we are going to define our integral here and call it a function of t, f of t. So that we define f of t as the integral from 0 to 1. Then we have x raised to power t minus 1 divided by logarithm of x. So we say that if we put t as 0, so that suppose we want to evaluate f of 0, then we shall get integral from 0 to 1, x raised to power 0 minus 1 divided by logarithm of x dx. Now, any number raised to power 0 is 1, so the numerator becomes 1 minus 1. The denominator is logarithm of x, and therefore we get the integral from 0 to 1 of 0. So when we integrate 0, when we work out a definite integral and the integrand is 0, then the result is 0. So we note that when f of 0, f of 0 is equals to 0. And now we have said that we want to use the properties of differentiation on this function. So we want to differentiate the function f of t with respect to t. So we write the derivative with respect to t of f of t. We are going to define, I'm going to denote this one by f prime of t, the derivative of the function f of t with respect to t. So in this case, we differentiate both sides of the expression with respect to t, and because the integral here is with respect to x and the differentiation is with respect to t, then we can change the order so that we can differentiate first and then integrate. So in this case, since the denominator is a function of x, then we can write 1 over logarithm of x, then the derivative with respect to t of x raised to power t minus 1. So when we are differentiating this function x raised to power t, minus 1 with respect to t, we see that we can write the derivative with respect to t of x raised to power t minus the derivative with respect to t of 1. Now, the derivative of 1 is 0. So we will be interested in finding out this derivative. Now, if we have a function, say I'm going to call it y, a function of t expressed as x raised to power t, and we want to differentiate this with respect to t, one of the methods we can apply is to take logarithm on both sides. So I take logarithm of y, which will be equals to logarithm of x raised to power t. And then we can apply the rows of logarithms on the right hand side so that we get t logarithm of x. And then differentiate now both sides. The derivative of the left hand side, we want to differentiate logarithm of y with respect to t, which will be, now because the derivative is with respect to t, the logarithm of x is taken as a constant here. So we write logarithm of x, then the derivative with respect to t of t. Differentiating t with respect to t, we get 1. And the left hand side becomes 1 over y dy by dt, which is equals to logarithm of x times 1. So that the derivative of y with respect to t becomes y times logarithm of x, where y in this case we had defined y as x raised to power t here. And so we can substitute and write that this is equals to, that is, the left hand side is the derivative with respect to t of x raised to power t, and this is equals to x raised to power t times logarithm of x. So we have that x raised to power t times logarithm of x. Another method is where we can just apply directly when we write this one, and we see that the derivative of minus 1 here is 0. To differentiate this, which we have obtained here, another method is by using the properties of logarithms by writing x raised to power t as e raised to power logarithm of x raised to power t, which we can then differentiate, and we end up with the same results. So in our expression here, we are going to replace this derivative. See that this derivative we have obtained x raised to power t times logarithm of x. So we're going to replace that quantity here, this quantity here. So we are going to get integral from 0 to 1 divided by logarithm of x times x raised to power t logarithm of x. And then we integrate with respect to x. This is our expression, which is f prime of t. Now notice that the logarithm of x here will cancel with this one, and so we are left with x raised to power t. We are left with f prime being equals to the integral from 0 to 1 of x raised to power t, and now we can integrate this with respect to the integral here is with respect to x, not t. So we have the integral from 0 to 1 x raised to power t dx. So when we are integrating a function x raised to power t, we are simply going to increase the power of x by 1. So we get x raised to power t plus 1 and divide the result by the new power of x. So we have 1 divided by t plus 1, x raised to power t plus 1. Then we can evaluate this when x is equals to 1 and when x is 0. So when x is 1, we have 1 raised to power t plus 1. 1 raised to any number is 1. And when x is 0, we have 0 raised to power t plus 1, which is 0. So in this case, we are getting, we are supposed to get something like, we have 1 all over t plus 1. Then we get 1 raised to power t plus 1 minus 0 raised to power t plus 1. And see that this is equals to 1 minus 0. So we end up with 1 all over t plus 1. So in this case, f prime of t is this. So remember, f prime is the derivative. Remember that when we write f prime of t, we mean the derivative with respect to t of f of t, which we are getting as 1 over t plus 1. So if we want to get f of t, then it means that we integrate our expression, which is 1 over t plus 1, with respect to t. So to get f of t, we integrate the expression that we have here, because this one is a derivative with respect to t. So meaning that if we want to find f of t, then we integrate with respect to t. So integrating this expression will give us logarithm of t plus 1 plus a constant. So this is f of t. But we had seen that f of 0 was equals to 0. So we can evaluate this function at t is equals to 0 and equate the results to 0. So when t is 0, we get that f of 0, which is equals to, now when we substitute here, we get 0 plus 1 plus c. So logarithm of 0 plus 1 is logarithm of 1, which is 0 plus c. So f of 0 is equals to c. But we had seen that f of 0 is equals to 0, which implies that c is equals to 0. Then we substitute back and we get f of t is equals to logarithm. We get f of t is equals to logarithm of t plus 1. F of t is logarithm of t plus 1. But what was f of t? F of t was the integral from 0 to 1, x raised to power t minus 1 divided by logarithm of x integrated with respect to x. This means that we can equate these two. So that we write the integral from 0 to 1, x raised to power t minus 1 divided by logarithm of x dx is equals to logarithm of t plus 1. So that if we now set a certain value for t, if we now consider the case when t is equals to 2, we can write the integral from 0 to 1, x raised to power 2 minus 1 divided by logarithm of x dx is equals to logarithm of 2 plus 1, which is logarithm of 3. So we can find the value of logarithm of 3. So our integral, which was the integral from 0 to 1, x squared minus 1 of a logarithm of x becomes a logarithm of 3. Becomes logarithm of 3. Notice what we have done here. We have considered the integral, a function f of t, which we have called the integral. We have defined as the integral from 0 to 1 x raised to power t minus 1 divided by logarithm of x. And we started by finding f of 0. And we saw that this will be integral from 0 to 1 x raised to power 0 minus 1 divided by logarithm of x dx. And x raised to power 0 is 1. So this becomes 1 minus 1 all over logarithm of x dx. And 1 minus 1 is 0. So that gives us 0. So that in this case, f of 0 is equals to 0. This is an important initial condition for that integral. We then differentiate with respect to t, the function f of t, which is the derivative with respect to t of the integral from 0 to 1 x raised to power t minus 1 or of a logarithm of x dx. And we saw that in this case, the left-hand side becomes f prime of t, which is so the derivative, which we can write as the integral from 0 to 1 all over logarithm of x d by dt of x raised to power t minus 1 dx. And we saw that when we differentiate x raised to power t, we get, when we differentiate x raised to power t, we get x raised to power t times logarithm of x. The derivative of 1 is, of course, 0. Then, logarithm of x here cancels out with the logarithm of x. And this will yield the integral from 0 to 1 x raised to power t dt dx. Then we integrate this to get x raised to power t plus 1 all over t plus 1, and x increases from 0 to 1. Notice that this is x increasing from 0 to 1, not t, because the integral is with respect to x. So that we get 1 over t plus 1, then 1 raised to power t plus 1, minus 0 raised to power t plus 1. And 1 raised to power t plus 1 is 1, 0 raised to power t plus 1 is 0. So that this gives 1 all over t plus 1. So the value of this integral is 1 divided by t plus 1, and this is now f prime of t, which is the derivative. To get f of t, we integrate both sides of this expression. So f of t, when we write now f of t, we integrate 1 all over t plus 1 with respect to t. And integration will give us the logarithm of t plus 1 plus some constant we can call c. This is f of t. And remember the initial condition. The initial condition is that when t is equals to 0, we have f of 0 is equals to 0. So that we can write from our expression here that f of 0, which is equals to logarithm of 0 plus 1 plus c, must be equals to 0. And this we get, from here we get c is equals to 0. Then we substitute back into this expression here. C is equals to 0. We have f prime, or rather f of t, therefore becomes logarithm of t plus 1. But we also know that from our definition, f of t was the integral from 0 to 1 x raised to power t minus 1 divided by logarithm of x dx. And therefore we equate these two, this one to this. This will give us that the integral from 0 to 1 x raised to power t minus 1 divided by logarithm of x. If we integrate that with respect to x, then we should get logarithm of t plus 1. So that now we consider the case when t is equals to 2 and we get the integral from 0 to 1 x raised to power 2 minus 1 divided by logarithm of x dx is equals to logarithm of 2 plus 1, which is logarithm of 3. So our integral which we wanted to find was the integral from 0 to 1 of x squared minus 1 of a logarithm of x integrated with respect to x, and we see that the solution is a logarithm of 3. Now we can consider a second example where we have to evaluate the integral from 0 to 1 x times logarithm of x, and we can consider an alternative integral which is the integral from 0 to 1 x raised to power t dx. This is based on the realization that the derivative with respect to t of x raised to power t. So the choice of this new integral is based on the realization that when we differentiate x raised to power t with respect to t, we get x raised to power t times logarithm of x. So basically we see that we can easily get the integral that we want by differentiating and then setting t as 1. So we therefore now consider this integral. Integrating x raised to power t, as we have seen, from 0 to 1 will give us 1 divided by 1 plus t, as we had done in the previous example. So we now have this integral, the integral from 0 to 1 x raised to power t dt, which is equals to 1 divided by 1 plus t. So if we want to get the expression we have here, x raised to power t, x logarithm of x, then we are simply going to differentiate so that we can get something like this. So we differentiate both sides with respect to t. So the left hand side, when we differentiate, we get x raised to power t logarithm of x. The right hand side we differentiate, we get minus 1 over 1 plus t squared. And then we set t as 1. So that will give us the solution, which is minus 1 over 1 plus 1 squared, which is minus 1 over 4. This method can be used to various integrals. We have an integral such as the integral from 0 to 1 sine of x divided by x. We can consider an alternative integral, and we set y to be the integral from 0 to infinity x sine of x divided by x by times e raised to power negative tx. Notice that if we set t as 0, e raised to power 0 is 1. So when we write sine of x divided by x, e raised to power negative tx, then we can set t as 0. And when t is 0, this quantity here becomes 1. So we end up with the expression we have here. So we see that to get what we have here, we just need to set t as 0. But now, if we take the limit as t approaches infinity for this function, the limit as t approaches infinity of e raised to power negative tx becomes 0. So when we take the limit as t approaches infinity of this quantity, then we get 0. So now, that is some kind of an initial condition. Now, if we go back to our function here and differentiate our function, which is y(t), which is the integral from 0 to infinity, sine of x divided by x times e raised to power negative tx. And suppose we consider differentiating this with respect to t, so that we write y prime of t is equals to the integral from 0 to infinity d by dt. Because we are differentiating with respect to t, then I'm going to write the sine of x divided by x first. Then the derivative with respect to t of e raised to power negative tx. And this should be the partial derivative to show that we are only considering t to be the variable in that case. When we differentiate e raised to power negative tx with respect to t, then we get negative x e raised to power negative tx. So this will give us sine of x divided by x, then multiplying minus x e raised to power negative tx dx. So x cancels out here, and then we have a negative, so I'll write negative 1 integral from 0 to infinity e raised to power negative tx sine of x dx. Then I'm going to consider, this is y prime of t. I'm going to consider the integration of this. I can first consider the indefinite integral e raised to power negative tx sine of x dx. This can be expressed using the d operator form as 1 over d e raised to power negative tx sine of x. Then we apply the rules of the d operator, the theorems. The theorem 2, which we write e raised to power negative tx. Then we have 1 over d minus t operating on sine of x. And this will give us e raised to power negative tx. Then we have d plus t all over d squared minus t squared sine of x. When we remember when we apply theorem, we want to apply theorem 3. So here we can first multiply the numerator and the denominator by the conjugate of the denominator. So we get this quantity here. And this will give us e raised to power negative tx. Then we have d plus t divided by minus 1 minus t squared sine of x minus 1 minus t squared. So I can write this is minus e raised to power negative tx divided by 1 plus t squared. See that I can factor out the negative here in the denominator. Then I have minus here. Then I have e raised to power negative tx. Then the denominator is 1 plus t squared. And then d plus t operating on sine of x. Now d sine of x will give us the cosine. D is the derivative. D is the derivative, so differentiating sine of x will give us cosine of x, then plus t sine of x. That is the expression. Then this is the expression, the indefinite integral of this function. So we are going to substitute back here to get y prime is minus 1 times the integral from 0 to infinity of this. So we're going to take the limit. So I'm going to write y prime when we substitute back. Substituting back, I'm going to get y prime of t is equals to minus 1. Then we have minus e raised to power negative tx, all for 1 plus t squared into cosine of x plus t sine of x. X increases from 0 to infinity. And we notice that when x goes to infinity, maybe before I take the limits, I can push the negative here in here so that it becomes positive. So write e raised to power negative tx divided by 1 plus t squared. Then we have cosine of x plus t sine of x. Then x increases from 0 to infinity. And now when x goes to infinity, you see that the exponential function will be 0. So this becomes 0 minus. And when t is 0, or rather when x is 0, this becomes 1. So I get 1 all over 1 plus t squared into cosine of 0 is 1 and sine of 0 is 0. So the result is which is y prime of t is equals to 1 divided by 1 plus t squared. This is a negative there. So if I want y of t, then I'm going to integrate this with respect to t, minus 1 over 1 plus t squared dt. The integral of this is minus tan inverse of t plus a constant. This is y of t. Now remember, we had that the limit as t approaches infinity of y of t, we had obtained this as 0. If you can recall that, somewhere we did that initially at the beginning here. Sorry. I don't know whether we had done that, but yeah, I think this was here. Yes, the limit as t approaches infinity, y of t was 0. So in this case, you're going to use that. We're going to use that one here. So we write the limit as t approaches 0. T approaches infinity, sorry. of y of t is equals to the limit as t approaches infinity of negative, I'll put the negative here. Then I have tan inverse of t plus a constant. So the left hand side becomes 0, which is equals to minus 1 times, if we take the tan inverse of t as t approaches infinity, we get pi over 2. Then we have plus c, and this means that c is equals to pi divided by 2. So this is the value of c. Then we substitute back in this expression here. So we write c as pi over 2, then we have minus tan inverse of t. So we can write y of t is equals to pi divided by 2 minus tan inverse of t. But what do we have initially? We know that y of t was from the beginning. We had taken y of t to be the integral from 0 to infinity sine of x divided by x times e raised to power negative tx dx. So y of t was the integral from 0 to infinity sine of x divided by x times e raised to power negative tx dx. This means that we can equate these two. So we write, therefore, this implies that the integral from 0 to infinity sine of x divided by x multiplied by e raised to power negative tx dx is equals to pi divided by 2 minus tan inverse of t. So we now consider the case when t is 0. When t is equals to 0, the left-hand side becomes integral from 0 to infinity sine of x divided by x dx, because e raised to power 0 is 1. The right-hand side becomes pi over 2 minus tan inverse of 0. But tan inverse of 0 is 0, and therefore this becomes pi over 2 minus 0, which is equals to pi divided by 2. So the integral from 0 to infinity, sine of x divided by x is equals to pi divided by 2. Now, there are various other methods that we can apply to evaluate this integral, including the use of Laplace transforms. This method, we are calling it the differentiation with respect to a parameter. So we first introduce another variable that acts like a parameter during the process of integration, then make use of the properties of differentiation to work out our expression. So this method, we call it the differentiation with respect to a parameter. Thank you for watching.